Good afternoon. We are talking about the lecture series on X-ray crystallography and solid-state chemistry. This is the 28th lecture, and it is on structure of solids. Well, we have been discussing many classes of compounds and their structures in last few lectures. Today, we'll start discussing 3 compounds which the mineral name is corundum, ilmenite, and lithium niobate. They are very closely related classes of compounds. Let's go to the compositional share of this corundum, ilmenite, lithium niobate. Okay, that's what we show in the table below, that corundum, which we can generalize as M2O3, and M could be aluminum, chromium, iron, titanium, vanadium, gallium, rhodium. Well, this corundum can have several modifications. Alpha alumina, which is L2O3, and if we dope this alpha alumina with chromium, we say this crystal a ruby crystal. And if we dope with the titanium, then it is a sapphire. So you can see how many different compounds we can have. And this is corundum type of structure, crystallizing in corundum type of structure. Well, ilmenite, we see that MO3 is there, but in case of M, there are 2 cations. M is magnesium, manganese, iron, cobalt, nickel, zinc, cadmium, even magnesium, tin oxide, cadmium, tin oxide, nickel, manganese oxide, sodium, antimony oxides. All these compounds do crystallize in ilmenite structure. And lithium niobate, as I said, and lithium tantalate. Okay. What we can really describe the structures as close-packed structure, and that is what is hexagonal close-packed arrangement of oxide ions with cations occupying 2/3 of the octahedral sites. If we take this structure, here is the structure, see, corundum structure. If we take this structure, we can conceptually say that they are related with nickel arsenide structure, which we have discussed in details, in which all the octahedral sites are occupied, and to the cadmium iodide structure, that what we also discussed, in which only half of the octahedral sites are occupied. The crystal structure is shown, as I say, shown here. If we take the crystallographic 3-dimensional arrangement of this structure, we can describe the unit cell as it's a trigonal, and the space group is R3C. And number of the space group is 167. So if it is trigonal, the cell parameter is there. A is equal to this, and C is equal to this Armstrong. And we can also say about the Wyckoff positions of these atoms, aluminium and oxide. Wyckoff position 12C, for oxygen, it is 18E. And then we know the if we go to the Wyckoff position, we can see the atomic positional system called fractional coordinates 0, 0, and 0.350 for jet, and that is 0.3060 and 0 and 0.25. There are some spatial position, or as well as general position too. Okay, so as I say, corundum contains only 1 cation, and that is aluminium, whereas ilmenite contains 2 cations, and here we see that one is M cation, another is titanium, magnesium, tin, cadmium, tin, nickel, manganese. That's what I said. Okay, and we have also discussed what about the cations and how they are positioned and how they are ordered. That's what we have discussed also. So lithium niobate, the same octahedral sites are occupied, but the cation ordering is, the arrangement is different. That's what we say that this is why you call these three closely structure are very much related to each other. Okay, if we look into the ilmenite structure, the same thing we can say. The space group is 148, number 148, and that is the cell parameters. Here we know it, and the YF position here. Iron is 6C, titanium is 6C, oxygen is 18F, and thereby the positional parameter of these atoms are written down here. One very important thing is that we have lots of software to deal with this unit cell and look it into various axes. So for example here, lithium niobate, we look at it here like this AB, 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 AB arrangement. And then you see, if we just change the, look through, this is what we look through C axis, that is mentioned. And if we look through B axis, we can see this arrangement also. So here, this is also a trigonal type of structure. Please note that all are trigonal, but different space group. So, and that is why we call it very closely related tree type of structure. Now we go to the next slides. Here we see covalent network structures. Three-dimensional framework of corner sharing tetrahedron. So in these materials are very strong directional covalent bonds, and that can also be described as a closed-back structure or eutectic structure, which we discussed in earlier lectures. Example of these type of covalent network structures are silicon carbide and diamond. Silicon carbide has got polymorphs. One of the polymorphs, silicon carbide, is like Hussain structure, which we have discussed. And they are silicon or carbon is regarded as backing atom. And net result is a three-dimensional framework, corner sharing tetrahedron. That's what we discussed. Here the structure look like. If we see the ball and stick model of silicon carbide, to look it like this. These are silicon, these atoms are silicon, and these black ones are carbon. And so that is what there's another type of structure, we say diamond. Diamond is also regarded as spheroid structure, in which carbon atom is a closed-back arrangement, half the carbon atom and half of the carbon atom are in tetrahedral size. So as these atoms are of similar size, so classification of closed-back atom or atom occupying tetrahedral size are equivalent. So that diamond is as an example of eutectic structure, which is used since diamond, all atoms are the same size, and therefore we cannot distinguish between packing atoms and interstitial atoms. You know very well that diamond is having a very rigid structure, cubic crystal lattice, where each carbon atom is bonded covalently. It is bonded as a sp3 hybridization of carbon, and it is a face-centered cubic lattice, and with the two atom bases, resulting incredibly strong, dense, and hard material with a high melting point. The carbon-carbon distance is 1.54 angstrom. Now we go for some key features of silicon carbide. The key feature, if we describe it in unit cell type, the silicon carbide, as I said, silicon carbide, there are polymorphs, and this 3C silicon carbide is known as beta silicon carbide. And beta silicon carbide is having a face-centered cubic structure, similar to zinc blende or diamond. Another polytypes is alpha silicon carbide. Here we are giving you some of the key features of structural features of beta silicon carbide. As we say, the stacking sequence is ABC, 3-layer cubic. And the space group here, that means that it's face-centered. There's bar 4, 3M, which is space group number 216. So as it is face-centered cubic crystal system, we have a cell parameter A is equal to this Armstrong, 297 Kelvin. But some reports said that the cell parameters ranges from 4.35 to 4.36. We have unit cell formula unit in the cell. Unit cell is Z is equal to 4, and silicon carbon bond distance is 1.89 Armstrong. And YF position is here, 4A silicon is 000 and 4 in 4C. Carbon is 1,4 to 1,4 to 1,4. We can shift this origin and start with the origin is 1,4, 1,4, 1,4 instead of 0, 0. And that means depending on the origin which you have chosen, we can place the YF positions there. And then you see here are, as I said, the two polymorphs. So one is cubic, another is hexagonal. It's hexagonal alpha silicon carbide is hexagonal. A schematic diagram of the packing atoms of alpha silicon. Here is the schematic packing arrangement. Here, packing arrangement will show this. And the cubic beta silicon, the packing arrangement. If we take the alpha silicon and its space group, we can see 186. Depending on 4H and 6H, we have the variation of cell parameters and as well as the formula unit in the unit cell. Z is equal to 6 in one case, and another Z is equal to 4. We go to the next one. Here we are talking about the same feature as we said, talked the diamond structure. That diamond structure, that is a ball and stick diagram of diamond structure, and you see we call it face-centered centered cubic Bravais lattice with 2 atomic base, which we discussed in the last slide. Carbon, silicon, germanium, and alpha-tin can get crystallized in diamond structure, and the space group of diamond is the space group number is 227, which is F, D, bar 3M. And if we talk about point group, we see that we have 6 2-fold rotation, 4 3-fold rotations, and 3 4-fold rotation, 9 mirror planes in inversion. And lattice constant, here we are giving the lattice constant of diamond. It is in nanometer, please don't note it, but that means it is 3.567 Armstrong. Silicon, cell parameter of silicon, cell parameter of germanium, and cell parameter of alpha silicon. And the formula unit in the unit cell is 8, and therefore you can find out also the atomic density and the density of the surface atoms. We can, if we take this plane, the surface density in this, we can calculate the density with this formula. Wyckoff notations here. If there are 2 sets of Wyckoff notation, face-centered translation, 0, 0 plus face-centered translation. If this is the origin, then we have other points, 0, half, 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 0, half, and half, half, 0. If we take the set number 2, and this, if this is the origin, and then we have face-centered translation, we get these parameters. Well, these 2 sets represent the 2 interpenetrating face-centered cubic sublattice that define the diamond structure. Okay, we take the next one. Okay, see, so far we are talking about covalent network structure, ionic structure, intermetallic structures, various classification, various compounds which are crystallizing in same type of structures. This is what we have discussed, and we also discussed the packing arrangement also. Now we have molecular structure. That can also be described as a means of packing atom, which many molecular compound crystallizes in closed packed structure. Though the bonding force between the adjacent molecules are very weak, van der Waals force, even then they can be classified, described as closed packed structures. Here we are taking some example. For example, here, if we crystallize hydrogen, it's we have to go for a very low temperature, methane and hydrochloric acid. So we can describe them also as hexagonal closed packing or cubic closed packing structure, but they can rotate and occupy different orientations at random. Okay, if we are talking another non-spherical molecules, though so far we assume that our atoms are spherical, but if non-spherical molecules that can also fit into a closed packed arrangement. If we take an example of aluminum bromide dimer of ALS Br3 is with two aluminum tetrahedra AlBr4 and sharing common edges. We can see that in figure A. That is what the figure A is. And we can see that atom 3 and 5 are bridging atoms for this. We can also discuss this tetrahedral sides of this packing arrangement. The dest atoms are below the plane of paper, and here is tetrahedral side. This is a tetrahedral sides plus, and this is tetrahedral side minus, and we can describe this crystalline arrangement, and also talk about how many tetrahedral sides are occupied. And you can see that 1/8 of the tetrahedral sides are occupied. If the hexagonal element of bromine atom, and then only 1/8 of the tetrahedral sides are occupied. So this is what is molecular structure we are talking about. So we see that metallic structure, ionic structure, a covalent structure, molecular structure, that what we can also describe in a closed packing arrangement efficiently, we say. And then we take another class of compounds, very important class of compounds. Let's take the source where I took this. This is what is published in Nature in 1991. So this is called fullerene C60. The scientist who discovered this molecule awarded Nobel Prize in Chemistry in 1996. It is a hollow structure, a spherical cage, and diameter of about 7.1 angstrom, formed from 3 coordinated, that means sp2 hybridization of carbon atoms, which is linked to a network of 12 pentagons and 20 hexagons. Do we see the pentagon and hexagon here? Of course, we do see the pentagon and hexagon here. Here, this is what is a hexagon. This blue, what is an hexagon, and then we see that pentagon here. This is a pentagon of carbon atoms. So a network of 12 pentagons and 20 hexagons. This figure A, which is C60 molecules, and then it was named for it is geodesic dome of Buckminster Fuller, and therefore it is in honor the compounder is called fullerene C60. The name C60 is fullerene in honor of Buckminster Fuller. In crystalline C60, the molecules arrange themselves according to the principle of closed packing, as I said, and that is a face-centered closed packing. The formula unit is 4 in C60, and the cell parameter is 14.17 angstrom. So that is a very hard molecule, and as I said, cubic phase diagonal corresponds to a closed pack direction, and we can calculate the adjacent molecule separately, which is I think 10.0 angstrom. You see, this carbon-carbon distance is 1.4, and this carbon-carbon distance is 1.45. So it is the contact is the short and the carbon-carbon bond. If we take the organic molecules here, if we come to the organic molecules, compared with this typical single bonding organic molecule carbon-carbon and carbon-carbon double bond, we see that 1.54 angstrom, and in case of carbon-carbon double bond, it's 1.33 angstrom. And therefore, we can see that in between this carbon-carbon single bond and carbon-carbon double bond, these carbon atoms and carbon atoms have this distance. Well, we continue with this one and see that fullerenes, as we said, that this molecule and is an ellipsoid, almost shaped like a raggy ball. Then it has got room for other atoms. So those octahedral interstitial sites in C16, if these are filled by large alkali atom cations, then we call this fullerized. Total class of compounds, we call it fullerized. And you can see that A3, which is fit in the tetrahedral octahedral sites of C16 packing, and this A could be, as I said, alkali metals, rubidium, potassium, and in which T plus and T minus, and that means tetrahedral and octal sites are occupied. The materials are metallic. Mind it, these materials are metallic, and alkali metals ions, and donate their electrons to conduction band of the C60 network. And we can have very many different types of fullerides. And their temperature, we can see that these fullerides are becoming superconducting materials. And the superconducting temperature is 45 K, and gallium, rubidium, C60. These fullerides existed with defined patterns of occupancy and interstitial sites. As I say, this is close packing, and we can compare this with rock salt and zinc blende analog of this as C60 and A2C60. Here you can see that the wide range of formula arises because the C60 molecules can accept a number of electrons to be announced. C60 N minus, if N could be 1, 2, 3, 4. And that is the excitement in C60 chemistry, and a large number of researchers throughout the world working with this in this type of compounds, fullerenes and fullerides. Okay, I showed the source where I took this also. With this, I think that I can finish this lecture. Today we need another lecture to complete the syllabus we followed for this lecture series, and that means the lecture number 29th. That is 29th lecture will complete the total syllabus we followed for the series, for this lecture series. And in this slides, you can see that we talk about flavons and isoflavons. Flavons and isoflavons are natural product, and this syllabus has got only one single classes of compounds, that is flavons and isoflavons, to be described as structures. Organic compounds, there are many solid organic compounds, and there are various classes of compounds, and their structure have been determined also. But the syllabus says only that we have to describe the structure of flavons and isoflavons. We will take these flavons and isoflavons in the next lecture and summarize the lecture series and finish the syllabus as we planned form. Okay. Thank you for your attention. Hope that we meet in the next and the last lecture, and within 2 weeks. Thank you so much.